take them down and take them down and take them down, take them down, take them down and take them down and take them down. As you look, the whole room explode down and as you look, the whole room explode down and
This talk is about schemas and queues, and I'm not claiming we invented any of those things, but we started using the combination of having a schema for your data and a queue-based system for quite a while, and we now want to re-architecture all of our stuff on this idea. And this is basically just a quick overview of what this actually looks like and what the idea behind it is. My name is Armin Ronacher. I'm a software engineer at a London-based gaming company called Fireteam, and we basically do computer gaming online infrastructure. And I also do a lot of Python libraries. Just to give you a brief overview of what we are actually doing so that you know what the use case is, we provide infrastructure for computer games so that you can upload your statistics, you can do matchmaking, all the sort of stuff that a multiplayer computer game needs these days. And it does this on both mobile devices as well as traditional consoles. So you have two very different use cases. On a mobile device, you want the ability to go offline at any point in time. So if a player plays his game and then enters a tunnel, the game should not stop responding. On a console or a traditional computer, you generally want to have a standing connection so that you can notify your friends when you go online and offline. So these are, one is a RESTful approach, where you basically just request response, modify stuff. And the other one is a stateful response, a stateful connection where the fact that the connection is established has a meaning in the system. And we love Python. So for a while, we already did something like what the slides are going to show you. But this particular incarnation of this queue-based approach is something we haven't tested at all yet. We have a working prototype, and it's amazingly fun to work with, but there are definitely many kinks that still need to iron out. And as I said, we probably didn't come up with this. All right, so this is all very abstract. What does it actually mean? First, to give you a little bit of the motivation behind of this, how many of you are using Redis? All right, how do you migrate Redis from one machine to the other without causing downtime? All right, so one solution heard from many people is use virtual IPs. So if you migrate over your Redis to a different machine, you just flip the IP address and then you don't need to update any configuration. The other solution is to restart your processes and point it to the new Redis installation. But generally it involves restarting something. And the problem with restarting something is that if we restart the machines that are connected to our consoles, all of the consoles would lose connectivity. If we restart the Python process that holds the socket open. So we don't want to do that. So that's one motivation behind the whole architecture we have, is we want to be able to replace everything in the infrastructure without ever causing downtime. And on the more levels we can actually do that, the better it is for us. And this also goes for any other database. The other motivation is, what if a user plays on a train and loses connectivity? Just to keep this in mind, this is one of the most important parts of your infrastructure. Is it should be able to continue operating under really bad circumstances. And this is actually the main motivation, is we want to use the exact same code for standing connections as well as RESTful connections. All right, so this is what we started out with. It's a very traditional request handling. You have a client that connects to a load balancer. The load balancer connects to Nginx. Nginx connects to UWSGI. Or if you would be using Rails, you would connect to, I don't know what you use in Rails now, something that speaks HTTP, and then there is your application code. It's a little bit annoying if you pull the plug between any of these components, someone will get a connection reset. A little bit of this connection reset sometimes is hidden because everything in the system buffers up a little bit of stuff, so you can send, even if something is disconnected, you can probably still send a little bit of data into a queue. So some network failures are kind of hidden. So our new approach, and what we started already doing for stateful connections before, is we connect from a client to a load balancer like before, and then we connect to what we call a concentrator, which keeps all the socket connections open. And then all of the data, instead of directly going to an application code, goes onto an actual queue and is then picked up by a worker and then goes the other way back. And what we started doing with this is by sharing a schema between the workers and the front end, which we call a concentrator. So the basic idea is we get stateful connections for free because the connection is established to the concentrator. So it doesn't matter if it's an HTTP connection or if it's a TCP connection, it stays open for longer. The client connects to the concentrator, the socket stays open, and whatever then happens with the socket is separate. Now, when I was talking about we want to be able to pull the plug at any point in time, there is a concept in computing that's very helpful for this. It's the concept of idempotence. It's the idea that you can execute an operation multiple times and it will not negatively affect the result. An example of a couple of idempotent operations is setting a field to a certain value. If you do this 100 times, the field will still have the same value. A set which can only contain each field once, if you add that field 100 times, it will not make your set any larger. Or deleting a record. If you delete 10 times, it still be deleted. If the client comes up with the ID for the object, I can create it once, twice, 3 times, and it will not create the object over and over again because it already sees there is an object with this ID and I have to create it. There are operations that are not idempotent, like incrementing a value. If I do that 10 times, I will end up with a vastly different number than if I would have only done this once, or appending items to list and so forth. So we try to keep as many operations as possible idempotent. That way, if there is a failure, we can safely tell the client to just try again. All right, so this is what the whole thing looks like. The first important part is a registry, where we register types and endpoints. Types are anything that flows through the system, and endpoints are functions that are exposed on HTTP. And this registry can be exported and picked up by another process. So the way this works is the worker code defines types and endpoints. And these are then shared with the concentrator. And they have then the same knowledge without actually being starting from the same Python process. So the concentrator boots up once, and it will find by other means the configuration from the individual workers. The types we define are composite types out of primitives and, well, composite types. And it's written in a way that you can stream in data. To give you a concrete example of what this actually looks like, for instance, if we have users that are exposed through our API, they have an ID, they have a username, email address, and so forth, and they're defined in the worker code somewhere. Then they are registered with the registry, and the concentrator later on picks it up. Each endpoint that is defined also has shows up in the registry. For instance, if we have a function that returns the current user data, we expose that endpoint under a certain name. We tell it the semantics, like the function to look up a user has select semantics, which means it will never modify anything. And then it returns a user schema. And this is roughly what the code looks like. It checks the permissions for that user and then returns the data. Obviously, select implies idempotence. And here's how the concentrator roughly works. It takes an HTTP request, it resolves the endpoint, it does a first level access check, loads extra state, loads the form data, and then puts it on an actual queue. And then waits for the result that the worker hopefully sends back. And because this is so separate from HTTP, it can actually do a lot more. Like you can have WebSockets, server-side events with this, and so forth. So the concentrator keeps the socket open, for instance, and you can send as many results as you want at any point in time into that socket, and the client will be notified. If you have ever used the Twitter streaming API or server-side sent events, it's roughly the same. You keep an HTTP connection open, and you just wait for results to come in. If my concentrator holds the socket and I do a code deploy, I'm just restarting the worker. Nobody ever notices that we didn't code upgrade. And because we can inject extra state into these requests, we can, for instance, say a client says, I want to use the latest version of the code, or I'm actually an old game, I want to use the version of the code you had a year ago. We just have to make sure that there is a worker open that can handle this request. So if we know there is a client that has a game that was released a year ago and they want to continue operating this, we can keep a worker open for that old code and it will still work. Same thing goes with any other information that would be injected. And the queue worker basically subscribes to a queue, gets an item from the queue, invokes the expected endpoint, processes the request, and sends it back. So far, the only difference between this and the regular approach is instead of connecting sockets together, where every failure will bubble up the chain, we are connecting to something that holds up information. And that's really useful for failure handling. So for instance, we don't have enough infrastructure in place, and the queue fills up. Normally, if you don't have enough infrastructure in place, eventually your server will stop responding to requests. And someone gets a connection reset or something of this sort. Because we have the queue in Redis or any other data store, we can see how filled up the queue is. And if it's too large, we can respond with proper error message and say, we can't handle more requests. We run out of infrastructure. If we have a failure anywhere on the system and we know it's an idempotent request, we can just fail and put it back on the queue and retry. So for instance, I have a worker that crashed, but I know it's an idempotent request. I just put it back on the queue and let another worker pick it up. I want to give you an example how this actually looks like, and I hope this kind of works. Just have to make sure that this is the same screen. All right, let's see if this works. All right, so this is basically all that's necessary. The first part is the concentrator. And in this case, it's, just open this in the proper editor. In this particular case, it makes a concentrator. It connects to an environment which defines where is my queue. It's basically an object that contains the configuration. And this is actually all the code that's necessary in a particular case. The other example is the actual worker. So we have one schema defined. We have one endpoint. It takes a user ID. It returns a user, has specific semantics, and then returns the data. And then it makes this whole thing and starts it. And I just want to show you what the actual effect of this is. So here I make my concentrator. And here I have my worker. And if I now do an HTTP request, see if I can make this. So I make a regular HTTP request and to get a user, and it returns this. But what's actually happening behind the scenes is we can monitor this on Redis. if I do this request, it actually goes through a Redis queue. So the first it does is it pushes a request on a default queue, and then it goes through this queue. Now, the interesting part is I can actually kill my worker here, and I do the request again, and nothing comes back. But when the worker goes online, my request immediately comes back. So, and the effect of this is I can do code updates without anyone noticing that anything ever goes down. All right. For this prototype and what we're also using in production for one part of the infrastructure is Redis. And there are tons of queue systems like RabbitMQ, ActiveMQ, Beanstalk, Kafka, whatever. Redis is actually really interesting if you want to do like a real-time approach where everything goes through the system. And the reason for this is that you can safely restart it, and it will remember what was in the queue and come back with this in a really fast way. So if I controlled shut down my Redis and I bring it back up, it works. I can even replicate this. So if Redis is my central queue system, I can set a second slave in it, and both will see the same messages showing up. So I can flip between multiple Redis installations without losing a significant number of messages. And due to how Redis persistent works, which is that every n seconds it dumps its state to the drive, it actually has a really interesting effect on queues. So if you have two Redis installations, one you have for the queue and the other one you have for everything else, the ideal queue is always empty. So for as long as you have more consumers than you have producers, your queue will always be empty or nearly empty. So what you're actually saving every 60 seconds to the hard drive is essentially an empty file, which makes it really fast. Whereas if you use RabbitMQ or Beanstalk and you enable durable mode, where it also dumps all of its operations to the file system, you notice that you get a much lower performance out of those. There is obviously the problem that it's a single point of failure, but you can sort of counter this by using multiple Redis installations and using Redis Sentinel for somewhat automatic failover. But with all of this, like with a schema system on the one hand and a queue on the other one, you get a lot of really nice things you wouldn't get otherwise. For instance, the last couple of days there were a lot of comments about trusting user input on Rails. And there are some really benign examples. For instance, if you go to Twitter, to the search page, and you add like Angular, you add brackets to the queue parameter on the page, you get an internal server error because the backend probably sees an array instead of a string. Because we have schemas for everything, you can transmit as much data as you want to me, and I will not fail over. I will not fail because the schema system properly converts the data as necessary. This also goes quite far in regards to countering possible attacks that would exploit my server resources. For instance, I don't know if you remember, but there was the situation which brought a lot of discussions up in regards to the security of hash tables, where if you would exploit that certain keys basically convert your hash table into a linear list. We don't have that problem because we know which keys we're expecting. So the keys we're not expecting, we're just skipping over. So you can try to exploit our server in that sense, but because we're just skipping past these values, there is no way for you to actually cause any significant damage on our infrastructure. And because all of the transport conversion is handled in the front-end server, you can write workers in arbitrary languages. So if we have a backend infrastructure that needs to talk to a PlayStation, which uses a binary pre-compiled library, which we don't have any control over, we can just write that part in C, and we'll register with the infrastructure and has the same external API. Yeah, and obviously zero downtime in regards to pretty much anything on the infrastructure. There's still certain things where a connection will break, but with much better control over this. All right, that's the basic idea behind this. And when I did the original slides for this, it was a way longer talk that actually went into the individual details of it, where it's really hard to fit this into 25 minutes. I do think, though, that the general approach is really interesting, and I would love to share some of how this works internally in a proper written document so that you could actually implement this on your own, and maybe it would make sense to open source some of this implementation. That's basically a very, very quick introduction in the idea of using a queue instead of sockets for an application deployment. Yeah.
Any questions?